Okay, so I am going to talk about the physics in Interstellar some way. I'll sort of jump around through that. One of the things that I hope you will understand by the time we're through with this is the difference between this kind of a representation of a wormhole, which is a two-dimensional kind of shadow of it, and what the artists and scientists behind Interstellar tried to do in the movie. So here we go. It is true, as Star Trek said, that space is still to a great extent the final frontier, trying to understand at a basic physics level what we mean by space and what it is and how it works and what our place is in it. Still a very, very deep part at the roots of physics. In order to talk about what we're going to talk about tonight, you need to establish what dimensions are to start with, because I'm going to talk about higher dimensions eventually. So dimensions are the number of different ways that you can point that are mutually perpendicular. Let me sneak up on what I mean by that. We know what we mean by a zero-dimensional thing is a point has no extension in any direction at all. If you take a point and move it in some direction, you describe a line, a one-dimensional thing. If you take that line and move it perpendicular to yourself, you sweep out a surface, a two-dimensional thing. And then if you take a surface and move it perpendicular to itself, you sweep out a 3D volume in that case. Before I go any further, and I can't see this very well, I got to do this check. Can't finish the talk without making sure you're all members of this secret club. And the secret club is those of us who are three-dimensional. So the way you establish this is extend a finger, and then extend your middle finger perpendicular to that, and then extend your thumb perpendicular to that. So now you've constructed something pointing in three mutually perpendicular ways. You think of dimensions being up and down, front, back, side to side. The point of this is it doesn't matter how you orient your hand. You can keep your fingers and thumb mutually perpendicular. And it turns out that only three-dimensional creatures can do this. So if you've done that successfully, I can continue to talk. Because, for instance, if you were just a two-dimensional creature, and I can't do this up against the slide here, but if I did a two-dimensional creature, I could do this way and this way, but I couldn't stay in a two-dimensional surface and point in another direction. So if any of you out there were two-dimensional, you couldn't do that third thing. And so that's the important thing to discriminate. Then we have a fourth dimension. Well, let's get a handle on that. So let's do this again. Point in some direction. Again, it doesn't have to be up and down, just some direction. And then point in a direction perpendicular to that. Now, it helps me an octopus. If you've got two arms, you've got to remember one of those directions. And then point in a direction perpendicular to both of those. And now point in a direction that's perpendicular to all three of those. Now, you see there are denizens out there who can somehow point in four mutually perpendicular directions. They have their own secret club, and we're not members. We're confined to a three-dimensional universe, and we are, as physicists, trying to understand what that means and what the implications are. So in this context, a hyperspace is more dimensions than the space you're considering. It's a very general and probably obscure definition, but it will become clear as I go along with what I mean by that. If we're thinking about a two-dimensional surface, then the third dimension is a hyperspace. If we're thinking about our three dimensions, then a higher dimension would be a hyperspace compared to us. It depends on relative where you're talking about. So let me go back into the history of this. It goes back into the 19th, early 20th century when Riemann and Lobachevsky first started trying to write down the mathematics of how you do geometry in a curved surface. That Euclid had done it in a flat surface, worked out all the geometry we learned 10th grade geometry, whatever you do it these days. But Riemann and Lobachevsky worked out how it works in a curved space. But as soon as they did that, people who were trying to follow along with this started asking themselves, well, the space curves, what does it curve into? And particularly if we live in a three-dimensional space that might be curved, what does it curve into? So these kind of ideas were very much prominent around the turn of the last century, and people explored them and thought about them, and they worked their way into art in various ways. So there's this famous little book called Flatland by Edwin Abbott, which is a wonderful, totally misogynistic little book. How many people have read that? Quite a three. Thank you. It's also been made into films a couple of times. And another thing that came out, it was already around, I think, for Riemann Lobachevsky, but people toyed around with this idea of a tesseract, which plays a role in Interstellar. So let me try to illustrate what a tesseract is at some level. It's a four-dimensional entity, but I want to start with a three-dimensional thing to try to illustrate what's going on in a picture I want to show you here. So this is where I need my lovely young assistant, Dr. Super Duper, to come up here and help just a second. If you could just hold on to this. So this is a three-dimensional box. It's got 6 surfaces, 4 around the perimeter, and a top and a bottom. So it's not quite a cube, but you get the idea. But I can sort of make a two-dimensional, this is a three-dimensional thing, I can make a two-dimensional representation of it by unfolding it. So I can pick up the top, and unfold it this way. I can unfold that side down. I can unfold this side here, and finally that side there, and I end up with a two-dimensional thing that when I unfold this three-dimensional cube into 2 dimensions, thanks, Jim, then I get something that looks kind of like a cross. Okay? So a tesseract is a 4-dimensional hypercube. Rather than 6 surfaces, it's got 8 surfaces, each of which is a 3-dimensional cube. And it's very hard for us poor 3-dimensional people with only this signal to flash to picture, but you can then unfold a 4-dimensional hypercube in your imagination and see what it looks like in 3 dimensions. And that's what Salvador Dali did in this famous picture, Corpus Hypercubus. So he shows Christ crucified on a cross. But if you look closely at that cross, it consists of 8 cubes. 4 going up and down. 1, 2, 3, 4. 2 on each side, 1 out the front, 1 out the back. So he's representing an unfolded 4-dimensional tesseract in 3-dimensional space. So it was, these ideas kind of permeated art for the first part of the century. So in our more immediate theme, then the backstory in terms of movies and how we got to Interstellar goes back to Contact. Well, so Carl Sagan actually wanted to make the movie first, and it got stuck in production hell, so he went off and wrote the novel, which is in fact a very fine piece of writing on its own. But he wanted to get his heroine from the Earth to Vega, and from Vega to the center of the galaxy or some such thing. And so he invoked what he knew about curved space and Einstein's theory, things like that. He invoked something called the Einstein-Rosen Bridge, which is a way of going down from one universe into another, or from one part of a universe into another. And he sent off to his friend Kip Thorne, who is the preeminent studier of general relativity of our generation, and been at Caltech for most of his career. And Thorne said, no, that particular idea won't work, that Jodie Foster will die a screaming death by being tidally pulled into a noodle and pulled apart, and that's not good for your plot. So no, you don't want to do that. But he worked out a new theory. He went up into an isolated cabin in Oregon, and he sat down for a couple of weeks and worked out a theory that you could open a mouth in the context of Einstein's theories. This is not a science fiction fantasy. This is something worked out in the context of the mathematics of Einstein's theory, that you could open up such a connection. This one would slam shut on you. When he first did it, it would be unstable. He had to devise something to hold it open. He invented something, or invoked it, he called it exotic matter. But it's quite related to an anti-gravity stuff, the dark energy that is causing the universe to accelerate now, which is a whole other story that we've talked about at AoTATX before. We'll probably do it again. I'm not going to go into it tonight. But there was, conceptually, he could do that, hold the wormhole open. It's not ruled out by physics. That's one of Thorne's criteria. So that's good enough for Sagan, wrote it into the book, put it into the movie, and off they went. So then that brings us to Interstellar. Turns out that Sagan, the producer of Contact, was Linda Obst, and Sagan introduced Obst to Thorne, and then Thorne and Obst devised the idea of Interstellar and worked on it for a long time. Spielberg was involved for a while, then stepped out, finally got turned into a good movie recently, and in that context, I already get that. You know what really holds these two movies together is this guy. We in Austin understand that. So let me talk a little bit about how wormholes work. Very hard to picture what happens when you're punching a three-dimensional thing through a three-dimensional space, because it involves hyperspace. It's punching through hyperspace in some sense. So physicists have invented an idea called an embedding diagram, which is a way of kind of casting a shadow from a higher dimension to a lower dimension, but preserving the basics of the geometry. So if there's a hole punched through it, the hole is still there. So here's a two-dimensional version of a large-scale space. Have to be curved in a funny way I don't need to go into, and then a tunnel punched through it. But the important thing about this representation of a wormhole is to understand what it is and what it isn't. What it is trying to represent a wormhole in a two-dimensional space, so we can stand outside it as three-dimensional hyperspace observers and see what it looks like. So that's like us up here. This guy here looking down on this surface and seeing this funny geometry through it. But to understand what a wormhole would be like to us, you need to picture yourself as a two-dimensional denizen of this two-dimensional space. And you have no idea what hyperspace is at all, any more than you can point to fourth dimension here earlier. So if you look at the geometry there, this guy looks in, he can see his partner down there looking back, he could look all the way through. Light could go through this. He could crawl along one of these lines. He's got to ooze like an amoeba because he's a two-dimensional guy. But he could crawl along there and go through there and come out the other side without having to go all that long way distance around. Basic idea of the wormhole. Another important idea, he could go in about halfway and then he could turn sideways and march off as straight as he could. And if he did that, he would go around what we perceive as the perimeter of that cylinder and right back to where he started from again. So it's all space. There's no matter. It's just curved space. But you go off as straight as you can. You come back to where you started from again. Space is curved in that way. But there's no wall. You just go off there and come back the other direction. There's not a wall to run into. And this guy would not see it as a tube. Again, the space through the middle here that I've indicated by the arrow, that's hyperspace. That's not part of their conception or perception at all. And so you do these embedding diagrams to kind of give you an idea of what's going on, but then it's easy to confuse a wormhole or a representation of a black hole of this funny curved space rather than the reality you're trying to portray. So here's back to something like what the reality would look like. Same two guys, now in three dimensions originally, with their flashlights, and they're looking at one another. And to illustrate this curved space, I'm showing this guy with a flashlight pointing down, and in this curved space, that light would go as straight as it can, but it would come back in the opposite direction and illuminate the top of his bowler. Or if he shined the flashlight off in this direction, it would come back and hit him on the other side. So no wall, just very curved space. So one of the lessons I'm trying to leave you with is you watch movies and TV programs, kind of watch to see when people are confusing this embedding diagram version of a wormhole with this real three-dimensional reality, in terms of how Thorne pictured this in Einstein's theory. Though it's not like a tunnel like that, it's a more complicated thing. Okay, so just a few movies and TV programs. I'm dating myself and how old these things are. You're welcome to bring more modern things to my attention here. But anybody remember Sliders? Yeah. No, Sliders fans here. That was a pretty good wormhole, because a wormhole is the mouth of it. It's a round thing in two dimensions, but it's a spherical thing in three dimensions. And Sliders caught that. You could go into that wormhole from the front, the back, the side, the top, the bottom. Sometimes they got a little bit of embedding diagram tunnel-like stuff to it, but actually they did a pretty good job with that. Babylon 5 kind of sucked. There was a ramp that had everything just going in one direction. Deep Space Nine was not too bad. They could go into that wormhole from any direction. It looked a little embedding diagram-like inside, but that wasn't bad. I thought Contact, Jodie Foster going through all that stuff, did a pretty good job. I was looking at it very closely yesterday because I was thinking of maybe trying to show one of these videos tonight. I'm going to run out of time. But in some places, as she's going through that thing, you can see the further reaches of the wormhole through the walls. And that's just a no-no. There's no walls to be seen through. It's all that curved space. You can't see through the wall to the further reaches of the tunnel. So that was a little disappointing. 2001: A Space Odyssey, the obelisk was actually a wormhole. of an odd shape. But who knows what went on there? Nobody's ever understood. And then just a comment about Stargate, wonderful program, but the idea that there's a two-dimensional opening through which they jump there, that's okay, but it's not an Einsteinian Kip Thorne wormhole. That would be a spherical thing that you would want to. Now, interestingly enough, Thorne went on, once he had this idea, to think more about wormholes, and then his colleague, Russian colleague, Igor Novikov, also elaborated on it. And I've got the Interstellar book here, but I've also got the popular books by Thorne and Novikov. You want to browse through them here at the front table. And it turns out that time, as well as space, connects differently through the wormhole. In Einstein's theory, the way Thorne worked it out and Novikov elaborated it, wormholes are automatically time machines. Very bizarre new aspect of it. Now, for time machines, in principle, you can travel back in time, in this theory, not before you made the wormhole. So Homer Simpson can't go all the way back to the dinosaurs if the wormhole were made earlier than that. But you can go in one mouth, come out in the past, go around in normal space, and meet yourself before you go in. You can have two of you. That's not prohibited in this theory. There are various time travel paradoxes, like the grandfather paradox. Travel back in time, shoot your grandfather before he marries your grandmother, so you would have never been born to be there to do it in the first place. Thorne said, leave granddad out of this. Go back and shoot yourself. Just a self-suicide paradox. And Novikov's brilliant addition to this was there is no paradox. That physics always works out so the paradox is avoided. And he found the flaw in the standard argument. The standard argument is to think of grandfather there by himself, and then he meets your grandmother, yada, yada, time machine, you come back. You have to have the time traveler in the argument in the first place when you first consider it. You can't consider granddad alone if eventually there's going to be a time traveler. So, grandfather's a young, spry guy. He ducks, and he punches out the time traveler. And no, he's not dead. And he goes on to, anyway. Very, very interesting idea. So there's a Novikov consistency conjecture that you'll never get, you can't travel back in time, you can't change the future. So here's a couple of films you can contemplate whether those are consistent or not. So here's the wormhole, the way Kip Thorne and their designers pictured it, looking into the other galaxy. Here, through the wormhole, and this is light bent around our galaxy here. Can we actually make wormholes? So Thorne did this in the context of Einstein's theory, but that leaves a big gap. Because it turns out we can't really establish whether there's a wormhole or not if we don't understand the theory of quantum gravity. We have to put effects of quantum theory, uncertainty, probability together with curved space. The best candidate for that right now is string theory. So string theory is something like a quantum gravity theory of everything. It is a quantum theory intrinsically, but it has curved space in it, like Einstein's theory of gravity. Particles aren't points, they're little strings of energy, vibrating in different ways. You get all the particles we know and love and more. But in this theory, which is an attempt to take a step towards proving whether wormholes can exist or not, it turns out that this theory has to have 10 spatial dimensions. So if you're having trouble pointing in 4 mutually perpendicular directions, you've got to imagine pointing in 10 mutually perpendicular directions. So physicists can do this mathematically, very hard to picture. And some of these dimensions may be, sorry, I keep hitting the wrong button. Some of these dimensions may be tiny and wrapped up like the inside of a wormhole. You go somewhere, you come around back to where you started from again. But there is a concept that you might have a very large 4-dimensional hyperspace in which you could embed whole universes. So now there are pictures of multiverses led by this idea there could be very much large extended hyperspace. Some of the ideas are you have a universe, has a black hole, collapses, rather than making a singularity, it makes something like a wormhole that goes off and makes a whole new universe somewhere. So these ideas aren't proven, but they arise out of the intellectual ferment of string theory and its attempt to construct a quantum gravity. So there's just a brief mention of the black hole Gargantua from the movie. Very cool job here done illustrating this. Thorne was very proud of working with the designers on this. So it's a rotating black hole. There's a little bit of left-right asymmetry that reflects that. It's a technical detail, but it's there. There's an accretion disk around it, a glowing disk some of that light goes down where we wouldn't see it, but it's curved around by the space of the black hole and brought up so that we do. So that's what's going on here. You're actually seeing light that wouldn't have come to us bent around by the gravity of the black hole. And then here is the tesseract scene from the end of Interstellar. So here's McConaughey in this tesseract, and it's got to do with this large hyperspace that is suggested by string theory. That's what they're alluding to. It's not only floating around in 3D and 4D, it's actually ranging in time as well. And of course he gets in there and he's tapping out the secret to quantum gravity to his daughter back in the time he came from. And how you tap out the secret of quantum gravity in Morse code 1 bit at a time, that's still a little obscure to me, but there it is. Here is a chance to really do this. The Large Hadron Collider outside of Geneva, there are chances that you could punch energy, gravity waves maybe off into a higher dimension. Very exotic thing, but driven by string theory, physicists running LHC are looking for such possibilities. Here's a notion. Look at that wonderful picture of the detector. And I'm sorry, I want to go backwards now to that guy. Don't you see a connection between that color scheme and that color scheme, or am I just making that up? Anyway, so there's the bottom line. Driven by all of this and string theory, there is some chance that hyperspace might be real, so keep an eye on this science as it progresses. Thank you very much.
We have some time for some questions. Shout out if you can't see you because the lights are kind of bright.
Anybody feeling hyperdimensional?
Okay, I see one at the top. Is that Spencer?
Yeah. So one of the things that Stephen Hawking has talked about is the feedback. And he talked about the light shining and coming back on the wormhole. Would that create like a feedback loop that would end up making it collapse or anything like that? Or would the light keep amplifying itself?
Yeah, that is the basic. A very basic point of why you need quantum gravity, and I left it out just for lack of time, so I'm delighted you have. So what Hawking is betting that wormholes can't exist, and Thorne's betting maybe they can. But Hawking's argument was that you can have a fundamental quantum energy around the mouth of the wormhole. It would go through the wormhole, then come around in normal space, back in the time just as it left, and now you have twice as much energy instantaneously. But then it does it again, comes back, and you have 4 times as much energy. It does it again, you have 8 times as much energy. So in no passage of time, by this argument of Hawking's, you can build up an infinite energy density, and that would slam the wormhole shut. But it turns out to prove whether Hawking is right or wrong about that argument, you have to have a theory of quantum gravity. So Hawking can speculate in that direction, but he can't prove it. Nobody can prove it yet. Can't prove wormholes can exist, and you can't prove they can't exist without this theory of quantum gravity. And that's the point that goes right to the heart of it. Thank you.
Okay, any more questions?
There's one down here, one on the right.
One down here, yeah.
So I've heard many times about the 10 dimensions of string theory being wrapped up in very small scales. But I've never understood how those can be independent of the 3 dimensions that we're familiar with. So if, I can imagine something wrapped up like in a loop, but that exists in our 3 dimensions. So what does it mean to say that there are other dimensions on a very small scale that are independent?
Could you repeat the question?
Yes, okay, so he's saying he doesn't understand how these extra dimensions could be there and wrapped up and not connected to this 3rd dimension. So the answer has to do with what you mean by a higher dimension. So if you picture a 2-dimensional space, so that's the whole 2-dimensional space. I can go in this direction or this direction. If I try to go in this direction, I'm going off into a different dimension. And then have that extra dimension, suppose it's a little circle. So I go off in that direction, but it just hooks around and comes right back where I started from again. But it does that action perpendicular to those 2 directions. So you have to use that extra dimensionality, which is absolutely perpendicular to the ones you're talking about. So the normal space is 3 dimensions. You have to do all of that extra space absolutely perpendicular to the 3. That requires you to be off in hyperspace. That's what drives the whole idea.
So you can move in these other dimensions while remaining stationary
yes, you could move in the extra dimensions while remaining stationary in the dimension we started from. Just as I could start from a two-dimensional space and go off into the space of this bar room and come back to where I started from. Fly around in that hyperspace. Next question.
Yes, there's one over there.
Could time be considered a dimension?
There is a sense in which time could be a dimension, but everything I'm trying to talk about here is real spatial dimensions. And then time also flows on, unless you have a wormhole, in case you can reverse and go back again. So it's still, certainly the wormhole idea complicates that. You could have time machines. But otherwise, in this context, it's not terribly useful to think of time as a dimension, although one can in a formal way and a very fruitful way in other contexts.
Okay, I think I saw a question in the middle. It's just there.
Could you quickly explain quantum entanglement?
I have a simple answer to that, and the answer is no. But let me elaborate just a little bit, because that's a really hugely important issue. So the idea of quantum entanglement is that at a quantum level things are described by waves, they're probability waves. But those waves can interact with each other, just like waves in an ocean can come along and reinforce or contradict one another. And so particles should be composed of those waves. And when Hawking invented his theory that black holes can radiate, he said, well, I can swallow one particle of a pair, and I can send the other particle out into space, and that latter will represent the black hole radiating. And theory kind of sat that way for 20 or 30 years, and people started thinking about quantum entanglement. With quantum entanglement, you can't ever really separate the ingoing from the outgoing particle. And to try to understand how one particle can get away and one can still be down there and coupled together, and what does that mean about an event horizon, and what does that mean about black holes in general, that's a problem. It's a smaller one than the biggest issues of quantum gravity, but that problem of how you do quantum entanglement around a black hole is just driving physicists nuts. Very, very deep problem.
Thank you.
You're welcome.
Okay, we have to move on, so let's thank Professor Compton again.